All right, welcome to week 5, Physics 11. Today we're starting a brand new unit, so we're never done with energy. Energy is always going to be a part of this, but we're on to a new topic, which is circuits. And to start out circuits, we're going to start out with the idea of current, because you can't really talk about anything electrical without talking about what current is. So what exactly is it? Well, current is just the rate of flow of charge. Well, what exactly is charge? So charge is the fundamental property of not all matter, but quite a few subatomic particles or atomic particles. So it's a fundamental property of some particles. Not every particle has this property. So some examples would be protons, electrons. Those are the ones that we'll be concerned about. So the symbol for charge, when we're using it in a formula, is going to be, sometimes you'll see capital Q, sometimes you'll see lower q. Both of those are the symbol that we use for charge in an equation. There's not really so much of a hard and fast rule for that one. The unit for that is a unit called coulomb, and the symbol for that is capital C. And if you want to look at the charge of one electron, just to give some idea of scale, the charge of one electron is 1.6 times 10 to the negative 19 coulomb. So it's a very, very small amount. Of course, if it's an electron, it's going to be negative. If it's a proton, it's going to be positive. So just a note there. Negative for electrons, positive for protons. So how do we measure current? Well, first of all, the device that we use to measure current is called an ammeter. So this is a device that we use. We plug it into a circuit, and essentially what it's doing, for all intents and purposes, is counting the number of electrons or positive charges. If we want to look at it, we'll see more about that in a moment. But it's essentially counting the number of coulombs that are passing a certain point. So I've got a quick video here that we can take a look at to help explain that a bit better.
Flows. If you picture the cross-section of a wire, you can measure how much charge flows through that cross-section over a period of time. The amount of charge moving past this point divided by the time period gives us a value in coulombs per second, which we call by the special unit amperes. So 1 coulomb of charge passing through that cross-section of wire over 1 second is equal to 1 ampere of current. Okay, but wait,
she says. All right, so let's go back here again. So we saw a few of those things. So the symbol for current is going to be I. So I comes from a French term. To be honest, the exact French word has escaped me, but the symbol for current in a formula is the letter I. This one will most of the time be just the capital I. There are some examples where it's a small I, but we'll get to that in a few weeks. The unit for that, which she also mentioned in the video, is the symbol A. Actually, let's just call it what it is here. So the correct term is ampere, but usually they're just referred to as amps. So like 1 amp, 2 amp. You've probably heard that various contexts before, and the symbol for it is a capital A. And the formula was also mentioned in that brief video. Current is the amount of charge divided by a certain amount of time. So how much charge is flown by an area divided by a given amount of time it took for that charge to flow. So here's a challenge, somewhat of a challenging question, a little tricky with the math. How many electrons are flowing past a point in the circuit each second if the current is 1 amp? So this is equal to the number of electrons in 1 coulomb of charge. So pause the video here and try and answer that question. Okay, if you're just coming back from pausing it, let's take a look at this formula. So we're essentially trying to find out how many electrons. And if we're measuring how many electrons, the question is really asking you what is the total amount of charge that flows by a spot if its current is 1 amp and it's traveling for 1 second. So let's rearrange this formula, I equals Q over T, and we're going to try and solve it for Q. So if we rearrange this, we're going to multiply both sides T, and then we'll have this Q, the charge equal to current times time. In this case here, it's 1 amp, and the time is 1 second, and that means there's going to be 1 coulomb. So 1 coulomb of charge is the total amount of charge that's transferred past a piece of wire if the current is 1 amp and it's been flowing for 1 second. Remember that an amp is also, just write this over here, 1 amp equals 1 coulomb in 1 second. Okay, so now we have this idea of coulombs, and now if you were trying to figure out how many electrons, this is where we use one of our conversion equations. So 1 coulomb, I'm going to multiply it by something that leaves me with electrons on the top and leaves me with coulombs on the bottom. So what do we know that converts electrons to coulombs? Well, we do know that the charge of 1 electron is equal to 1.6 times 10 to the negative 19 coulombs. And so if we have our formula here, we have 1 divided by 1.6 times 10 to the minus 19, and that's going to give us 6.25 times 10 to the 17. So this is the number of electrons that would flow past the circuit in 1 second. So obviously measuring in coulombs is a much more useful unit than measuring in amps. Oh, you have a 2 amp hot water kettle, for example. That's a lot easier than saying it's a 12.5 times 10 to the 17 electron per second the electronic device that you're looking at there. So this is the unit that we use. We use coulombs because counting electrons would be obviously very, very tiresome. So I'll pause or please pause the video here. Let's try answering example 2 and example. Okay, if you're back after pausing it, hopefully you did pause it, hopefully you did give it a try. How many electrons are in 20 coulombs of charge? Well, the same idea here. We have 20 coulombs, and we're going to multiply by 1.6 times 10 to the negative 19 coulombs for every electron. And so 20 divided by 1.6 times 10 to the minus 19, that's going to give us 1.25 times 10 to the 20 electrons. And the current is 0.85. What is the charge flowing in 1 second or in 10 seconds? Well, we are trying to find out charge. And so we have this formula rearranged for charge. We're going to have charge equals current at time. In this case here, it's going to be 0.85 amps times 1 second equals 0.85 coulombs. And then in 10 seconds, well, we just multiply the time by 10. So that would be, for this part here, 8.5 coulombs of charge. Now, just to give you an idea of scale of this as well, we've talked about how an electron is 10 to the negative 19. 1 bolt of lightning is around 2 coulombs. So 0.85 amps it's a fair amount of amps. You wouldn't want that going through you. That would be quite hazardous for your health. Okay, so we kind of have an understanding of what current is now to a certain extent, and we're going to try and build a circuit to see if we get what it looks like in a practical sense. So we're going to build a circuit here with a battery, a light bulb, a switch, and wires. So let's click on the link here. The link is also on your worksheet, and this is going to be your homework. So just follow along with me and we can see how this works. So we're going to plug in here a battery, and we said we wanted a light bulb in here, and we are going to want a switch in here. Let's put the switch over here, and we're going to need some wires to connect it. So let's connect a wire from here to here, and we'll connect a wire from here to here, and we'll connect a wire back from here to here. So now we've got our total circuit, but it's not quite running yet. So why is that? Well, it's because we haven't closed the switch. So let's close the switch and see what happens. Switch is closed, and now what we can see is we have current flowing. Now I'm going to show you a couple things here. So first of all, this is current flowing. So what do we need? The question on the sheet is, what do we need to make a complete, or what do we need to have for current to flow? Well, to make current flow, we need 2 things. So we need a complete path, and we call that a circuit. We need a complete path. So if the switch is open, for example, we can see that there's no current flowing. When the circuit is closed, we have a complete path and we are able to flow. And we also need a source of potential difference. And this potential difference is sometimes just referred to as voltage. So we need a source of potential difference. Now, I'm not going to go into too much detail with this, but in a short sense, voltage is sort of how much energy you're giving to each bit of charge. So it's 1 volt is 1 joule of energy for 1 coulomb of charge. It's how much energy we're going to give to each little ball of charge, in this case the ball that's flowing around the circuit. Now, if you look back at the demo, we'll go there in a second, there's an option to toggle between electron flow and conventional current. So what are those? Let's take a look here. And let's go over it in the top corner here. So this is electron flow. And you can see the electrons are flowing counterclockwise around the circuit. Let's switch it to conventional current. And now you'll see that conventional current is showing these arrows moving in a clockwise direction as opposed to a counterclockwise direction. So they are flowing in opposite directions. Let's go back to our sheet here. So what are those? Well, electron flow is what's actually happening in the wire. So in a conductor, so a conductor is something that allows electricity to flow freely. In a conductor, which are metal generally speaking, except with a few exceptions, conductors have fixed positive ions. You can see them here, like a fixed positive ion, these red dots here. And those don't really have a chance to move around. Now, in a metal, the electrons are what are called delocalized electrons in a conductor. And what that means is that these electrons are free to move about. They don't have to stay. This electron, for example, here doesn't belong to this proton here. It's free to move about. Sometimes this is referred to as a sea of electrons. So electrons are free to move, even though the positive nucleus of the atoms isn't free to move. Some of the electrons, not all of them, but some of them are free to move. So some of the electrons will be trapped and they can't really leave those positive ions, but some of them are able to move. And that's what's actually happening in the circuit. So electron flow is the flow of electrons, which are negative in a circuit. And in this case here, electrons go from, if we look at a battery here, let's say this is a battery like you've seen before, this is the positive terminal and this is the negative terminal. Well, electrons are going to flow out of the negative terminal and towards the positive terminal. This is what electrons will do. Now, conventional current it's just that, it's a convention. It's what essentially the world has decided to do, and we've kind of left it there. So Benjamin Franklin was the person who sort of had this understanding, or I mean, a lot of people had this understanding before him, but Benjamin Franklin was very famous, very influential, and he made a decision that he thought that the charge in a circuit was positive charges leaving the positive terminal. So if we draw our battery again, this is the positive and this is the negative end. What Benjamin Franklin thought was that positive charges left the positive terminal, wrapped around the circuit, and came back to join the negative. Now we know this isn't true. We know that the positive ions are not able to move. It's only the negative charges that are able to move. So in the piece of wire here, there's going to be a bunch of positive charges. But these positive charges in real life are not actually moving. It's really the negative charges that are going to be moving in this direction here, but the positive charges are stationary. So this is what we know is happening, but what Benjamin Franklin thought was happening was that these positive charges would be moving from positive to negative. So this is false, but I guess the world is too lazy to change their understanding. For whatever reason, we have all decided to kind of go along with this lie, and when we're talking about conventional current, we are saying that it's the flow of positive charge from positive to negative. So this is what we're all pretending is kind of happening. Now, to be honest, it doesn't it doesn't make any difference. If we talk about electrons flowing, for example, in this demo here, we can see electrons are flowing counterclockwise, conventional current is going to be clockwise. It really doesn't matter for any of our equations. So whichever way we look at it, you would still get the right answers for all of your questions. However, with that being said, in this class, unless otherwise stated, we will use conventional current. It just makes our life a lot easier to think about positive charge moving around as opposed to negative charge moving around backwards. But both are correct in their own way. And it's fine to use either one, and conventional current's the one that pretty much the whole world has decided to use. So what I want you to do, because I'll just let you know, as you probably have already guessed, physics teachers in general are not very good artists, and so if you have my level of artistry, we'd have a pretty rough time all trying to draw our circuits out using pictures of the different devices in our circuit. So what we have all done as scientists, as engineers, as physicists, is we've made up a system of schematic symbols. Now, these schematic symbols are just easier ways of drawing out the device compared to drawing out a realistic depiction of what those things look like. So, for example, in a schematic diagram, a wire is just a line, very easy, and a wire carries current throughout a circuit. So if we look at this demo over here, we can see that there's two buttons on the bottom right hand side. There's this one here that's currently toggled that shows the devices, and there's this one here which shows these as schematics. So this is the schematic for a light bulb, for example. Let me just open this switch here. There we go. We're opening the switch. Now we can see these symbols a bit better. This is the symbol here for a cell. Now, it's unfortunate, but the whole world uses this device here. Let's go back to a picture. The whole world calls this thing here a battery. Now, as a physicist, if we're being technical, it's not a battery. This is what we call a cell. Now, if you want to separate these, you just need to kind of click the junction here at the scissors that will separate it. If I want to make a battery, from a physics standpoint, a battery is a collection of two or more cells. So this symbol here, with two cells in a row, this is what a battery symbol is. It could be two or more, and a cell is just a single one. So what I'm going to do is I'm going to get you to pause the video now, and I want you to look at all of these different symbols here: battery, light bulb, resistor, switch. There's other ones here, but just the ones that I've listed on this sheet here. So wire, cell or battery, light bulb, resistor, and switch. I want you to go through these. The voltmeter, I'll show you the symbol of that. So the voltmeter is a circle with a V in it, ammeter is a circle with an A. This measures voltage, or I'm going to be a bit more precise. I'm going to say measures potential difference, and this measures current. Okay, so can I get you to pause the video and come back when you have gone through the FET display or the demo and filled out these symbols and made your best guesses as to what these actually are. Okay, so hopefully you've filled out this table for yourself, but here are the symbols and what they do. So wire is a straight line, carries current throughout a circuit. There's a picture of the schematic drawing of a cell or a battery. This provides a potential difference, which is commonly just written as PD, or also referred to as a voltage. A light bulb looks like this symbol here, it provides light, obviously. A resistor, you probably would have not really known what this was unless you tried putting it into a circuit and seeing the effect that it has. So you can try playing around with that, but what a resistor does is it reduces the amount of current. And then for a switch, there's two symbols. This is when it's called open, and this is when it's closed. And they refer to how the circuit is. So a circuit like with the switch in this position here is called a closed circuit, meaning it completes a full loop. And an open circuit would be like this, meaning it does not provide a full loop. It's not closed. Okay, so there's two ways that we can attach a device or devices in a circuit, and they are listed here. So first of all, there's a series circuit, and a series circuit, essentially, there is one continuous path from, I guess you could say, from positive to negative on the battery. So what this would look like if we were going to draw a battery of 2 cells connected to 2 resistors in series, that circuit would look like this. We've got our battery made up of 2 cells, and it's connected to resistor 1 and resistor 2, and it's in series. So you can see there's only one path for the charge to flow through, and so there's only one place for the charge to go. We're talking about conventional current, positive charge flowing out of the right-hand side through the 2 resistors back to the negative terminal of the first cell. Now, parallel has more than one, so multiple 2 or more paths for current to flow. And so if we're going to draw a battery of 2 cells connected to 2 resistors in parallel, well, that circuit would look like this. So one path is going through the resistor here, and another path is going through this resistor here. So there's 2 different paths for the current to flow. And these both relate to the homework assignment which we have. So if we go over here to our homework assignment, these are a couple of the circuits that I've asked you to build. This is a series circuit. I've left it opened so that you can't see what's going to actually happen and make those measurements yourself. You will have to build this yourself to get the answers. And this is a parallel circuit. So again, I've left it open up at the top here so you can't cheat. And so this is going to be your homework, is setting up these 2 circuits and making measurements of the current and answering a few questions revolving around that. So this one here would be a parallel circuit. This one here is going to be a series circuit. Okay, so that's to do with your homework. And that is it for this lesson. So you've got these practice questions. I encourage you to give those a try. Maybe not all of them, but at least the first half of them. The first 4 of them would be a good start. If you want to do more, by all means do so. And then the homework completion is building parallel and series circuits. And I want you to learn about current in both of those types of circuits. So I hope you enjoyed this week's tutorial, and email me if you have any questions.